So, this is again outline. Now, the first thing your book is going to sort of lead you into is what's called the octet rule, okay? Now, I'm going to call it slightly differently because I hate the octet rule, right? It's a terrible way of calling it because it has all these exceptions that way. So, what I'm going to call it is Nobel-like, okay? So, everything wants to have a Nobel-like configuration. What the octet rule is that the electron arrangements actually want to be like the nobles. Everybody know what the nobles is in the periodic table? Okay, it's that last column. Remember that? Okay. Now, if we look at period 2, which is the majority of the chemistry happens on the periodic table, how many electrons do you have on that period? How many elements do you have? 8. And so that's where the octet rule comes from. So the things on period 2 want a valence shell that has 8 electrons in it, okay? And that's going to be your most stable arrangement. Now, the exact location of a given electron outside the nucleus is actually going to be incredibly difficult to determine. What ends up happening is electrons are always popping in and out of existence and moving little short jumps very, very rapidly. And so you can't actually pin down an electron without an incredible amount of effort and energy, okay? Very difficult to do. So what we actually do is we're going to track the places they tend to be, okay? And so instead of trying to track like one person in a city, what do? You track the city, right? And we talk about San Francisco and California, the state, right? New York, both state and city. Yeah. And so when we find something that's very difficult to keep track of, we're going to talk about the area. And this is going to be called the electron cloud. That's where you have a 90% chance of finding that electron. Okay? Now, because electrons are going to be charged, they're going to be in constant motion, they're going to possess energy due to both of those reasons combined. And so this is always going to give them energy levels they're going to exist in. Okay? Kind of like saying that you possess more energy when you're on the 3rd floor than the 1st floor, right? Now, electrons can only occupy certain energy levels. These are going to be steps on a staircase they can't occupy between. In case you're wondering, this is quantum mechanics. That's actually what that is about, right? That they're split up into quanta, quantizable amounts, okay? Now, in general, electrons are going to occupy the lowest energy level first. Think of it like ground level, okay? So when we're talking about our periodic table, remember how it's period 1, 2, 3 as we go down? Okay. That period 1 is actually the lowest energy level. It's like going into the 1st floor, right? And then period 2 is actually a higher energy level. It's further away from the nucleus. And it's going to be going to a higher energy level, a higher floor. Okay? So what happens if the floor comes out from under you? We're up at floor 3. We're all going to fall, right? Because we're going to go to the lowest energy level possible, right? Why are we not going to the lowest energy level possible right now? Technically, the energy levels below us, directly below us right now, are full, aren't they? Yeah, that's the floor. Okay? And so electrons are going to experience essentially the same thing. Is you're going to fill the floors below it first, the space in between the nucleus first, and that's going to keep these other electrons out. If you have something that pulls those away, they're going to collapse down, aren't they? Okay? So you always have to fill the lowest energy levels first. Now again, unlike a real staircase, the energy levels actually are going to get closer together the further you get from the nucleus. And so what we're going to see here is that this analogy is going to break a little as we go out. And that's because our floors are actually just going to get packed closer together. Okay? And that's because we're dealing with 3-dimensional space. There's more space every time we go further out, right? Okay. All right, so this is what the energy levels look like in terms of your staircase, if you will. So right here, this is that first energy level. We call that the first period on the periodic table, okay? But you can call this the first energy level, first period, first shell. There's actually quite a few names. Principal quantum number, though we'll not cover that in great detail in this course. And so this would be the second energy level, second period, third energy level, third period. Notice again, our periodic table is actually flipped in terms of energy levels, right? Okay. Or another way of saying is it's listing from lowest to highest. All right, so the maximum number of electrons. Oh, so late. I don't know. Okay. I'm going to keep going because I have no idea what's going on with the thing. So the maximum number of the energy of electrons that can be found in any given energy level. This can always be calculated by formula, which would be 2 times n to the power of 2. So n is the number of the energy level. So for example, we're on period 1, that's going to be energy level 1. We'd put 1 in here. And so 1 to the second power is 1. 2 is the number of electrons that can go in the energy level. Notice if you look at your periodic table, how many elements are on the first period? 2, because that's the number of electrons that can fit in there, isn't it? Yeah. So we look at the second period of the periodic table, and we see n equals 2. So we would go 2 to the power of 2, that's 4, right? Okay. And then we times 2, and that's 8. We look at period 2, how many elements are on that period? 8. And so our periodic table is actually always has been telling us the structure of these electrons. That's how it's structured. You can fit 2 electrons in the first period, you can fit 8 in the next one, and then you go down, you can fit 8 again because that next energy level is a little wonky. And then you can go down to the next one, you can fit more, right? 18 in that case. And that's because you're further out. Now, if you use this formula, what you'll see is that this is where the periodic table kind of looks different than what you'd expect, right? And that's because n equals 3. 3 to the third is, or 3 to the second, is 3 times 3, 9, you got. And times 2, 18. And so you're expecting 18 on period 3, but you don't see 18 elements, do you? Okay. What you notice is period 4 is actually where 18 elements show up, right? Okay. So this is actually how that works out right here. Right here we have the element, we have the group number, and then we have the total number of electrons right there. And that's the number of electrons that can be in that energy level. And what you see is that hydrogen and helium actually fill up its energy level. Helium being a noble gas. And so that is the maximum amount of electrons that can exist on the first period, And we go down here and we see the maximum number of electrons that can exist on the second period is 8. And so we fill that one up with 8 more. Notice, however, the total number of electrons. When we filled up 8 electrons in the second period, how many total do we have? 10. What's going on? So what this looks like is we have our nucleus here. It's way too big, but you guys can still see that one, right? I can't write it small enough to actually make sense. So. Okay, the next one we're going to do is this is going to be period 1. Okay? And so that would be like a hydrogen if we have 1 electron. That would be like a helium if we have a second electron. Okay? Okay, so we try to put another electron in there. If I try to squeeze in another person in those desks right back there with you two, is that going to work out well? No, they're going to be repelled, aren't they? You're going to kick them out to this next level, aren't you? Okay? And so the same thing happens here. If we try to squeeze in another electron, whoop, it can't get in there. There's too much negative charge. So it's going to be repelled. It's not going to be allowed in. And it's going to go to the next period. Okay? And so that's where your third electron would go. Now you look at that period, it is bigger, isn't it? It has a lot more space in it, doesn't it? Okay? And that's because you have a lot more area, right? And And so as we go further from the nucleus, we're going to have more space to fit more electrons. And that's again what we're seeing in that n squared number. That's also what we're seeing here. So for example, this one here has filled in the second period, but also has a full first period. Can everybody say that okay? Technology doesn't work a lot of time around here, does it? No. Okay. Oh wow. Oh wow.
They had to rush this finish the school because they had to get students in it because they wanted to hit
Oh no.
COVID and wanted to hit and destroy 2 schools.
Hmm.
And they had to basically displace a bunch of people trying to fit people in schools, so they had to rush this school in 6 months.
Oh shoot. Okay. Wow. No one. Yeah, that makes a lot of sense.
It didn't work well. They had to replace the HVAC system, the Wi-Fi's. They had to replace a lot of things because they did not go well the first time.
That makes sense. Okay, so this is some more elements. Now we're on group number 2. We see here we're on magnesium. And we're going along that next period. And again, what do you see is that you have that next period that has been added. However, note that on period 3, you actually have added another type of orbital. You've actually added more space. It should be able to accommodate 18 electrons, as we talked about before. But has anybody ever noticed that like there's weird spots in rooms that nobody tends to sit? Like that desk right there in the first row right next to the TV, right? Nobody tends to sit on. They're high friction points, right? They make life a little less pleasant. And so what ends up happening is that extra 10 electrons worth of space that's added on period 3, it's so high energy and such weird shapes to fit in with the rest of the stuff that it doesn't actually get occupied until period 4. Okay? And so that's when you actually start occupying it, is when you go to period 4. And that's what you're seeing right here, actually. Okay, now again, your book calls it the octet rule. I'm going to call it Noble-like configuration. Is everybody okay with that? It's going to have a configuration with a number of electrons that would be the same as the noble gas. Okay, so you can always figure out what that would be by just looking at the noble gas in the periodic table, counting from the left over to the right on that period. And that's the number of electrons that's going to be there. Okay. My rule works a little easier, doesn't it? Octet only works on 2 periods. All right. So again, being able to locate the number of electrons present in each energy level is going to provide insight into how elements in a period or a group are related to each other. What you'll notice is that when you go down a group, they have similar electronic configurations, similar spots those electrons are going to be in. And so they end up with similar chemistries. Elements in the same group on the periodic table are going to have, again, samest number of electrons, but in the highest energy level. Okay? It's the outside, remember that. So think of it a bit like this. When you're trying to like manipulate things, like your keyboard and stuff, do you reach down into the keyboard to manipulate it? No, that doesn't make any sense, does it? Okay? What do? You manipulate the surface, right? Okay. Same thing happens in reactions. You're always going to be working with and manipulating the outer electrons. The stuff in the inside, past those outer electrons, they're going to be very hard to get to, right? And so you're going to have very little interaction with those. Boron, B, and aluminum have 3 electrons in their highest energy levels. These are both in group 3A. They tend to have 3 electrons. They're going to do things like bond, they'll lose those electrons, etc. All right, so the highest energy level that contains electrons is going to be called a valence shell. Valence literally meaning stuff on the outside, right? So it's the outer shell. The electrons in them are going to be the valence electrons. So those are the electrons in the valence shell. They're the outermost electrons. They're the ones you're actually going to interact with most of the time. The valence electrons are going to be farthest from the nucleus, meaning they're the weakest attached as well. So they're the easiest to actually strip off and do things with. These electrons will combine when elements make compounds. They're the ones that are going to make things like bonds. They're the ones that are going to get lost when we do ionic bonding, all that sort of stuff. Groups, the columns, are going to indicate the number of electrons that are in the atoms, the valence electrons in the atoms for your main group elements. Now, main group is the first 2 periods typically, though 3 periods is oftentimes used as main group because they tend to have all the same sort of chemistry, right? If you just look at the valence shell, if you just look at that group number, you're going to be able to see the valence shell electrons right away, right? So for example, we look at fluorine. What's the group number above it? 7. If you were to count from the left over to the right for fluorine, what would you get? 7 again, right? And so the number of valence electrons for fluorine is 7. Okay? And that makes doing chemistry very easy. Now, periods, the rows, is going to indicate the outermost energy level that contains electrons. So we're on period 1, that's going to be energy level 1, right? Period 2 is energy level 2. Period 3 is energy level 3, etc. Okay? There's currently only a period 7, though that may actually change in the near future if they manage to make the next element, because we're right on the edge right now. So that'll be interesting. Okay, so this right here, again, is the periods. Those are the energy levels. Right here, we have groups. These right here are the main group elements. They're denoted by the 1, 2, 3, 4, 5, 6, 7, 8A. They're what gives the name octet. Okay? Okay. Anybody know why they're the main group elements? If you look up to here, that's about 90% of all elements in the solar system. Okay? So 90% of the mass of the solar system, right there. Right? Actually, if you look up to here, that's about 70%, because the sun is the largest amount. So there you go. Now, elements in group 8A, those are going to be your noble or inert gases. They're on-reactive under all but extreme conditions, though the ones lower down in the noble gases are more reactive. They're easier to do stuff with. The noble gases are going to have 8 valence electrons. Helium is the exception because it only can have 2 valence electrons. It can't fill up anymore. Okay? And we're really just talking about the first 3 periods here. Where the octet rule holds true. Note that, realistically speaking, if you go into medical, most sciences, you will never see the lower element periodic table for the most part. Like, not a lot happens there. It's only very few select scientists that you heavily would use that stuff. Okay? And then you'll have a lot more chemistry. So, yay. All right. Now, possessing that noble-like configuration, that's a highly stable configuration for an atom to possess. So when it's noble-like configuration for its electrons, it tends to be very on-reactive. That's actually one of the reasons the noble gases are so on-reactive. They're already in noble-like configuration. So to achieve a valence octet, some atoms will give away electrons. Others are going to take electrons or accept electrons. Others are going to share electrons if they can't pull them away from the other. The different modes are going to achieve a valence octet, are going to lead to different kinds of compounds. And my thing's gone again. Ah, come on, man. Was this working better when I just used my own dongle? Yeah, for some reason, this one just does not want to go. weirdest part is I have the exact same hub for my computer in my office. I don't know why it causes so much trouble here. Okay. So if an atom loses or gains electrons to achieve an octet, this newly formed particle is going to have an unequal number of protons and electrons, right? And that's going to mean it's going to end up being charged. Now, we call charged atoms ions. That's the name for that. So if you have an unequal number of protons and electrons and you have a net charge on that atom, it's going to be an ion. Now, if you have a negative charge on it, it's called anion. So one of the ways you can kind of remember this for yourself, if you have a positive charge, it's going to be called a cation. If you have a negative charge, it's called an anion. Cats are positive, ants are negative. Okay? Okay. Anybody have any questions about that so far? All right, again, if you have a positive charge, net charge, it's going to be called a cation. The ion that has the same number of electrons as the nearest noble gas is on the periodic table is going to be called isoelectronic, iso meaning same, electronic, same electron configuration, as that noble gas. And so that is isoelectronic. Notice that the terminology I've been using here has been very independent of which direction I'm moving on the periodic table, hasn't it? Okay? So for example,
So you said positive charge cation. What's the negative?
anion. Yeah. Easy way to remember is ant or anti. Okay, and so you can go both directions on the periodic table. Remember, the periodic table just wraps around, right? It goes 1, 2, 1, 2, and then 3, 4, etc., and then it goes up to the next number, right? So it just wraps around. Okay, so you can go either direction when you're gaining or losing electrons. When you gain electron, you become isoelectronic to the stuff on the right. When you lose electrons, you become isoelectronic to the stuff on the left. Okay? And each time, you're just going to move towards the nearest noble gas. Okay, so let's talk a bit about polyatomic ions, and then I'll show you the periodic table with these trends. An easy way to remember this is the groups 1, 2, and 3 tend to move to the left. Those are also the metals. They're the things that tend to lose electrons. Okay? The stuff that's groups 4 and above, they tend to move to the right, 4A and above. And that's because they're actually closer to the noble gases on the right, aren't they? Typically. Okay. And so the polyatomic ions, these are going to consist of groups of nonmetals. These are going to form an ion. The charge is going to be the charge for the entire group of atoms, and they're not going to be able to be easily split off. Okay? An example of a polyatomic ion, have you ever seen carbonate, CO3-? Or heard of it before? Maybe? Ammonium? Hydroxide? Yeah. Lye? Soda ash lye? Potash lye? No. Okay. That's sodium hydroxide and potassium hydroxide. But you've heard of a few polyatomic ions, especially if you've ever looked at the products you're using. You would have seen those, okay? Okay, so let's look at the trends real quick. These are the overall trends, and again, you're going to notice these trends are going to exactly follow that same sort of trend we had been talking about with moving to the right to become isoelectronic to this group, moving to the left over here to become isoelectronic with, again, this group, right? So let's look at nitrogen. How many spots is nitrogen away from being a noble? 30. And so we want to gain 3 electrons, right? Because this is a larger number. And so if we gain 1, 2, 3 electrons, we become isoelectronic to a noble gas, don't we? Okay. And so what charge does nitrogen typically pick up? 3 minus. Gains 3 electrons. Phosphorus, same thing, right? Yeah. And these are actually where the group numbers come from. is they have the same sort of chemistry because they have the same number of electrons they want. Okay. Oxygen, well, we're 2 spots away, right? So how many electrons does that tend to pick up? 2. We look over here at the halogens. They're all 1 spot away, and so we tend to gain how many electrons? 1 again, don't we? Okay. Okay, over here we see the metals. These are the group 1 and 2 metals. And so these ones are going to typically lose an electron because the easiest way to get isoelectronic to group 8 would be to lose 1 electron to go this way. That making sense? You're going to go left on the periodic table. Okay, so group 1A tends to lose 1 electron. Group 2A tends to lose 2 electrons. Again, these are patterns. You see these blank spots here? They're things that don't typically just lose or gain electrons. They're more often used in like bonding. We'll talk about bonding in a bit, okay? Right now we're just trying to lose or gain electrons. It's called ionic bonding. Okay. Notice the transition metals over here. They do not have nice little patterns, do they? No, they have like 2 different charges they can be. Everybody see it okay? Okay. And so, for example, this one, these are the types of chromiums you actually might need if you're like eating it for nutrition. There's also a hexachromium, by the way, that's toxic, highly toxic to you. So, anyways, these are the transition metals here. Most of them have multiple charges they can be. And typically it's like a 2 to 3 plus, or a 1 to 2 plus. But some of them can be 4 plus, 6 plus. Yeah. And so they have a few other things they can do there. And this is because they have a lot of orbitals. They have a lot of places electrons can be. They're very, very close together. Do you remember where we were talking about the steps get shorter as we go up? Well, down here, the steps are pretty short. And so you have some very close spots you can be. They're very energetically similar. Okay, and these right here are going to be some of the different ions you can see. These ones are the polyatomic ions right here. Notice right here, for example, is the hydroxide we had mentioned before. Over here is ammonium. Anybody ever heard of ammonium before? You know Windex? Yeah. So it's ammonia-based cleaner. It's actually in the form of ammonium hydroxide that has its ammonia. That's how you get liquid ammonia. This one here is nitrates. You guys maybe have heard of nitrates. It was a big thing about like farming and soil. Okay. Anyways, this is carbonate right here. These ones you kind of have to semi-memorize because without semi-memorizing them, you're going to have a really difficult time whenever they come up. Okay? But there's patterns within it. If you look at this right here, nitrate, I8, is the larger number of oxygens. Nitrite, I took a bite, is the smaller number of oxygens. That's one way you can kind of remember that. As long as you remember one of these, you can remember both because 8 versus 9. Okay? Mm-hmm. No. Only really, really important ones that have like their own long cutouts. I might ask you 1 or 2 questions on an entire exam on that. But keep in mind, we have like 40 questions on exam typically, 30 to 40 questions. Can you fail that based off of 1 question? No. So keep your studying in mind that like if you spend 3 hours studying something that can only ask 1 question, like very niche, versus like general terminology, it might not be worth it, okay? But I do have a tendency to ask like 1 or 2 reading questions on the exam. Okay. So these are some different carbons. This one's bicarbonate, by the way. This is baking soda, in case you're wondering. This one's cyanide. Anybody ever heard of cyanide before? Yeah, like like cyanide poison. Yes, that's cyanide. It tastes very sweet, by the way. It does. It's actually quite pleasant, I imagine, to eat. Never tried it. I'm good, thank you.
How do you know what it tastes like?
People have been poisoned about it and report. Plus, how you mask it is you actually put like it in very sweet drinks. Otherwise, you can taste it. Yeah. So, like wine is a very popular drink to poison with cyanide. So, mhm. It is. Yeah. Yeah. It is indeed. It stores really well. It actually stores really, really well. So, this is acetate. That's vinegar. That's probably the most important one. I don't know why I don't lead with it because every food you eat around here has acetate in it, has some sort of vinegar in it. I don't know what it is. That's lactate right there. These are the sulfur ones. So this is, for example, hydrogen sulfate. That's phosphate, like the backbones in your DNA. That's the phosphate group right there. Okay. Now let's talk about naming ions. So for metal ions, we're going to add the word ion to the name of the metal. So for example, if we have sodium ion, we're just going to call it sodium ion. I know, it's really, really, chemists really make the naming difficult, don't we? Okay, so if you had iron and it was an ion, what do you call it? Iron ion. Magnesium? Magnesium ion. I know, so tough. Terrible, terrible. Okay, so transition metals actually have to have one more piece of information. So the iron actually you have to know what charge it is. Because iron 2 plus versus iron 3 plus is going to give you different chemistry. It's going to give you different compounds. Like I was talking about hexachromium, if you eat hexachromium, you're dead. If you eat chromium 3 plus, you're fine. You actually need some of that. And so it very much matters here, right? What we do when we have a transition metal, something that can have multiple different charges, we indicate the charge using Roman numerals. Does everybody remember Roman numerals? Okay, and how do we get 4? Yep, line V, right? Put the line in front. How do we get 6? VI, put the line behind. Very good. Okay, that's about as far as these ions are ever going to go, so there you go. Right here is 2 plus charge on iron, and that's iron 2 ion. So for the nonmetals, we're going to add the suffix. We'll replace that last part of it to indicate that it's an ion. So for example, on the periodic table, there's fluorine. And so that's going to go to fluoride. And that tells us it's the ionic form of fluorine. The polyatomic ions, most of them end in ate. The ending "ite" is actually used for related ions that have one fewer oxygen atom, literally to indicate that we're one fewer oxygen atom. Okay? And so you have the one that is the most prevalent. That's the one with the most oxygens. That's 8. Then you have "ite," which is going to have one less oxygen every time. Okay. Right here we have some important ones. These are hydroxide, hydronium. This is, have you guys ever heard of acid before? Okay, this is how the H plus actually exists in water. This is how what acids actually make in water. This right here is going to be cyanide. And those are some exceptions to this. Everybody notice the negative, positive, negative charges on these? Where is that negative charge located? The whole thing. Okay? That whole thing together is negative. This right here, that whole thing together is positive. Okay? Same thing for this. And that's how the polyatomic ions work. It's going to be the whole polyatomic ion is positive or negative. Okay. Now let's talk a little bit about ion formation. Right here we have some common cations and common anions. These are some common sources that you can find them in. For example, table salt is NaCl. This is going to be where you might find them in a like biological context. For example, does anybody know how CO2 is actually transported out of your body? No? Okay. Who here kind of thought it was hemoglobin carries it out? Don't feel embarrassed. Like a lot of books actually say that. So if you look in biology books, they will say that. And that's just outright a lie. That's wrong. Okay.
What's
Um,
hemoglobin?
huh?
What's hemoglobin?
Hemoglobin, it's your red blood cells. So you know how your red blood cells are red? That's because of hemoglobin. That's what actually carries the oxygen in your blood. Okay. The stuff you find in meat, by the way, is called myoglobin. It's the same sort of thing that like a baby uses myoglobin. Parts of your muscles use myoglobin, and that's why you find it in like treated meat. It's not hemoglobin, which is your blood. So
Is not good.
it is not at all.
It's not.
Yeah. It'll feel brutal. You literally will not be able to breathe enough. So you'll feel like you're suffocating, even though you're breathing as much as you can. Okay. Hemoglobin is what carries oxygen in your blood, and what your body then uses the oxygen to convert like glucose and such to energy, and a whole bunch of other processes. But that's the main one you're probably thinking of. And then what happens is you produce CO2. You then breathe the CO2 out. Okay. How you actually transport CO2 in your blood is you actually make what's called carbonic acid. This right here is the anion of carbonic acid. That's actually how it's transported in your blood. Okay? It's done by an enzyme that operates 1,000,000 times a second. It's incredibly fast. Right? So it literally makes an acid, it gets transported to your lungs, it converts it back to CO2, you breathe it out. Okay. Neat, huh? Look at that. We learned some biochem. Okay. Let's talk about how electrons transfer. Now, when it comes right down to it, a lot of these processes happened a long time ago. So, like, you're going to find NaCl in seawater, in mines, salt plains, etc. And this process happened millions of years ago, okay? But we're going to talk about like they're happening today because some of them still are happening today. So when a metal and a non-metal combine, electrons are going to be transferred between the atoms. They're going to form oppositely charged ions. The attraction of your cation and anion is actually what we refer to as an ionic bond. It's literally one is negative, one is positive. They're going to be attracted together, right? And so that is what we refer to as an ionic bond. Notice it's not really a bond. It's just two magnets being attracted together. Okay? They're not sharing anything, nothing like that. These are known as ionic compounds, and they're literally just arrangements of positive, negative. They're trapped together because they're positive and negative charges, and they're attracted together. Okay. Usually they're going to be repeated units. So if you were to actually look at these, it would not just be one pair. It would be repeated ones. This is negative. And over and over and over. Positive, negative, on and on. Okay? And so, for example, when you look at salt crystals, you can get like really big salt crystals, right? Everybody's seen that? They have a tendency to feed them to like horses and stuff. Yeah. That would be one big ionic bond system where they're all bonded together. Okay? Okay, so let's talk about the formula of an ionic compound. Now, the number of ions that can be combined for an ionic compound is going to be determined by the charge of the cation and the charge of the anion. And again, this is going to create a formula. It'll have a formula weight based on that formula. The cations and anions are going to combine, so the compound has a net charge of 0. if it has an overall charge, it would repel each other, right? And so, for example, if you had an overall charge on salt, table salt, they'd repel each other, and every time you open it, it would like go poof and boom and shoot in your face, right? Because they'd all be positives or they'd all be negatives. Okay. And so, again, the net overall charge tends to be 0. When the writing formulas for chemical compounds, we can represent the number of each particle in the compound with a subscript. The charges in the formula of the ionic compound are not going to be shown when we're in an ionic compound because we bounced them out. Okay? We no longer need to show that. Let's go ahead and practice. You'll notice this is very similar to cross multiplication. Anybody done cross multiplication before? Is that still a thing in math classes? Like, I do have to be really careful with that because they just wholesale get rid of entire things in math classes now. You'd all be really shocked about how much math has changed over the last 5-10 years. Okay, so this is how we're going to check a chemical formula. Number 1, determine the charge of the ions from the periodic table if they're main group elements. So, for example, what charge does oxygen want? 2 minus, right? We look at the periodic table, it's 2 away from being a noble gas. So it wants to go right 2, gain 2 electrons. Okay, what charge does aluminum typically want? Left 3 or positive 3, right? So 3 plus. All right, so we're then going to combine the ions in a formula. So the total charge presents sums to 0. So we need to have something that adds up to be 0. We're going to check the formula by examining the charges on the ions and subscripts in the formula. Okay, so notice that if we ever have something that's not equal and not a simple math problem to do, we can just do cross multiplication, can't we? And you can always do this and just divide so you get the lowest common denominator. Okay? So let's go ahead and look at this with aluminum 3 plus and oxygen 2 minus. Is everybody okay with how I got those charges? Did I lose anybody on that? Okay. Okay. So when I write these as a chemical formula, I'm going to take them down. I'm going to write them together. And what their subscripts need to be is what will even out that charge so the overall charge is 0. And how I do that is I take 2 from here, I write it over here. I take 3 from here and write it down here, right? And that's cross multiplication. Everybody see that okay? Okay. And then if I happen to have a common denominator, like I did that 2, 2, then I just divide by 2, don't I? And that'll give me 1, 1. Or if I had done this for something that's 3 minus and 3 plus, I could do 3, 3, and then go, oh, those are both 3, aren't they? So they're a 1-to-1 ratio. Okay. Okay. Anybody have any questions about that so far? That's how I get the chemical formula for aluminum oxide. So let's talk about some more of the rules to predict the number and charge in a chemical formula. Rule 1, the formula of the ionic compound has no net charge. You have to have all your positives and negatives add to 0. If we're going to have a net charge, it would be represented right up here. And it would list it. We'd have a 1 plus, 2 plus, some sort of net charge. Typically, they do not. The charge of the anion is typically the one that we know because it's usually something that's easy to figure out from our periodic table. Okay? Like if we have oxygen or nitrogen, what would the nitrogen charge be? We look at our periodic table. It's 3 from being a noble, and so that would be a what charge? 3 minus, right? Yeah. So typically you look at the anion first, you look at the nonmetal first. It's going to be the one that's easier to figure out what the charge could be. To name an ionic compound, the names of the 2 ions are going to be combined. You'll put the cation first. The word ion is going to be omitted in this case because it's denoted by the second one. And so, for example, right here, we have sodium and we have chlorine, right? So this one's going to end up being the cation because on the left, it's a metal. That's going to be sodium. We would normally call that cation sodium ion, right? We're going to drop the ion. So sodium. This chlorine right here is going to go to chloride because it's going to be the anion, okay? And so we get sodium chloride. You all already knew that one, didn't you? Yep, heard sodium chloride before. Isn't that interesting? That's why the name was like that. Didn't even know, did you? How about magnesium and fluorine? Magnesium fluoride, you got it. And once you get the trick of it, actually becomes like super easy, right? How about potassium and nitrogen? Potassium nitrite, you got it. Yeah. So once you get that trick down, it's going to be very easy. Again, it's a language thing. And so typically just practice is what's going to get it down for you. Because we're learning the language of science right now. So if a polyatomic ion is present, the name of the ion is going to remain unchanged in the name of the compound. So right here we actually have calciums, and then that's the polyatomic ion phosphate. And so what we're going to end up with is calcium phosphate. Okay, let's talk about transition metals now. So transition metals can have several different charges, right? And so they can have several different formulas, okay? So like, for example, copper here, they're one each because that was a 2 plus, that was a 2 minus. Does everybody know how I got that so quickly? I looked at the oxygen, didn't I? And when oxygen is always 2 minus. And so the copper has to be 2 plus because there's no charge. Okay, and so I'm going to again look at this. I'm going to go oxygen is always 2 minus. The copper has to be 2 plus, doesn't it? And so the actual name of that is going to be copper, Roman numeral 2 for the 2 plus charge, and then oxide. Okay. Everybody have that okay? Again, you can use the information about the non-metal portion, the anions, to figure out the cations. Okay? And that's typically how you're going to identify these charges on these cations if you have to. Okay? Which is when they're transition metals. That's when you have to identify those. So non-metals combine by sharing valence electrons to achieve an octet. You actually already saw this because we talked about polyatomic ions, didn't we? Notice those couldn't be combined using the same rules as we talked about just now, could they? Huh. So this PO4, how they're combining together, those phosphorus and 4 oxygens, is they're sharing electrons together, okay? And that's how they're gaining their octets, their noble-like configurations. Is one of them the oxygen, one of them the phosphorus, shares an electron, combines it together. That's going to give us a covalent bond. And by sharing those electrons, they now have the 8 electrons associating with each that they need. Okay? So the nonmetals are going to combine by sharing valence electrons. This will help them achieve their noble-like configuration. Excuse me. So sharing electrons is going to result in the formation of what's called a covalent bond. Literally, co, 2, right? Valences coming together, bonding. So we're sharing those electrons to create a bond between the two. Okay? It actually tells you everything about it. Now, the valence electrons in the bond are going to belong to both atoms. So they're going to count on both of the atoms in terms of have they filled their octet? Have they filled their noble-like configuration? When atoms share, the result is going to be a covalent compound. And so it's different than an ionic compound because they're sharing electrons between. Okay? Much like if you are holding on to something and somebody else is holding on to something, you guys are bonded together, aren't you? And if somebody drops off the mountain, you can hold on to them and keep them from falling, right? Okay. Now, The smallest or fundamental unit of a covalent compound is going to be called a molecule, and this is actually where that name had come from. Those were the molecules that you may not have realized before. Okay. So let's talk about naming ionic compounds a bit more. The number of covalent bonds that an atom will form is going to equal the number of electrons that are necessary to complete its octet. So how many bonds does an oxygen want? 2. It's the same rule, isn't it? You just count over to the nearest noble. And so how many bonds does a carbon want? So we look at carbon, we count over to the nearest noble, and it is 4. You got it. You got it. How many bonds does a boron want? Oh, I made a trick question on you. Uh-oh. So we look at boron, and how many electrons does it have in its valence shell? 3. And so it can only actually share electrons 3 times. Okay. It wants to make 3 bonds. The other way you can look at it is it goes left 3 times on the periodic table, and that gets you to a noble, right? Okay. Now, the use of electron dot symbols was first developed by the chemist G.N. Lewis. That's why it's going to end up being called Lewis structures in a little while. And again, these are going to show how atoms are shared, these electrons, to form their covalent bonding. So the electron dot symbol for any atom is going to consist of the element symbol, and then we're going to put dots for each of the valence electrons around it. To complete the octet through a covalent bond, an atom must share its unpaired electrons with another atom. And so then it will have that total number of electrons shared is going to end up being its complete octet. That's how it will fill in that noble-like configuration. Now, a shared pair of electrons, this can be called a bonding pair or simply a bond. This can be represented typically by a dashed line connecting the 2 electron dot symbols. This right here is a bond. Can everybody see it okay? You guys have all probably seen this before, right? Yeah, okay. Now, your book says, and it's not wrong, you've probably heard it from other teachers, that you can put 2 dots between 2 symbols, and that represents a bond. It's not wrong, but it is heavily, heavily, heavily discouraged. Okay? And the reason why is that it works pretty well when I'm typing things like this, right? That's pretty nice, and you can read that. Yeah. What happens when you do it quickly on your paper? Do those ever end up nice and vertical and you can actually see the dots? No. They always end up as a mess, and you can never read what you did. Okay? So I'm going to say right now, don't do this yourselves. Don't do it. Use the lines. Okay, so bonds are now lines to you, right? Never use 2 electrons in a pair to represent a bond. Okay? It's just going to cause you chaos. You're going to mess up a bunch, and you're going to get a bunch of things wrong. Okay? Don't do this. It's bad. Naughty. No. Okay? This one's good. Right. So these right here, anybody know what those are called? Those are Lewis symbols, right? Okay. And so we write out the symbol off the periodic table. Then we fill in around it with the number of electrons in its valence shell, right? And so we look at chlorine. The number of electrons in its valence shell is 7. Everybody see it okay? Okay. You actually want to write them individually first and then pair. Everybody see it okay? Okay, so what's happening here? Well, we're actually joining these electrons that are single ones to form a bond, aren't we? And so we join those together. That gives us our bond right there. These right here, they are not in bonds. Those are called lone pairs. So those are lone pairs of electrons. The ones that are in bonds, these are going to be shared pairs of electrons, or another way of saying that is covalent bond. Okay? And so those are covalent bonds. Notice again, this now has octets for both of these, doesn't it? by sharing, we now have a full valence shell. All right, now let's ignore carbon for a second. We can see the electron dot symbols that nitrogen forms 3 covalent bonds right here, oxygen 2, fluorine 1, right? Everybody see those okay? That's where they have the unpaired electrons, right? Okay. Now, fluorine, chlorine, bromine, these all typically share 1 electron. Okay, hydrogen shares 1 electron and forms 1 covalent bond typically. Why does it only do 1, by the way? You see how small it is? It only has room for 1 more. Okay, so it can only make 1 more bond here. It's just too small to accept any more bonding. Okay, now carbon actually has to form 4 covalent bonds to complete its octet. And so it can form 4 single bonds, it can form a double bond or 2 double bonds, it can form a triple bond. And so these right here are single bonds, these are double bonds, and these are triple bonds right here. See how we just add more lines to it? Okay. Again, we're always going to end up with 4 bonding pairs. Okay. Now, I'm not going to complicate it or go into much detail on this. If you're interested in it, talk to me. But you can actually make bonds with a single electron. You guys will never see it, ever. Okay? But it is something that can be done in the universe, right? But for you, from now on, bonds have how many electrons? 2. Okay, if you see a bond, it has how many electrons in it? 2. If you see a double bond, it has how many electrons? 4. Just double that, right? And then how many electrons in a triple bond? 6. Very good. 6 electrons. Okay. So this right here is the typical bonding that you see in the different groups. Notice that group 5 can actually form, like nitrogen, can form double and triple bonds. When we look at oxygen, it can form double and single bonds. And again, it's just the number of bonds, right? Okay. So let's talk about some different formulas and structure of covalent compounds again. The molecular formula for a covalent compound is going to identify all the components of a molecule. So for example, right here we have glucose, and it has this formula. Everybody knows glucose, right? Okay, it's the sugar that your brain uses. This tells us the molecule has 6 carbon atoms in that glucose. We have 12 hydrogen atoms. We have 6 more oxygen atoms, and that would be glucose. Can you have a glucose that has 5 carbons? No, glucose cannot have 5 carbons. It can only have 6. If it has 5 carbons, it's probably ribose, as in ribonucleic acid, like RNA. Molecular formulas of covalent compounds do not reduce to the smallest whole number ratio like those for ionic compounds, because that would be a completely different compound. Remember that when we're talking about ionic compounds, they're just repeated units, right? So if you have 20 sodiums and 20 chlorines versus 1 sodium, 1 chlorine, it's the same compound. You just have more of it, right? When you're talking about a molecule, on the other hand, if you had 20 carbons here, that is not glucose, is it? It's probably a fatty acid, actually. So you can't just multiply or divide these numbers in here. That would completely change the identity of this. Okay? Okay. In fact, there is a sugar that is C1H2O1. That is a compound. It is not something you want to eat. Okay? It's actually toxic to you. Okay, again, the formula does not show the structure, so the electron dot symbols can help us visualize what this structure would look like and help us write it out in a way that we can actually explore what it structurally looks like. Okay, methane, this is going to be a molecule with a formula of CH4. Everybody knows methane? Yeah. like the natural gas, right? Okay. Typically about 60% of natural gas. Natural gas is typically a mixture of methane up to propane. Okay. Um, so again, this is a covalent compound. They're all nonmetals. How can you tell the difference between a covalent and an ionic compound? What's sort of the easy way to separate those? What did the ionic compounds always have? They always had a metal in them, didn't they? Okay. If it has a metal in it, it's probably an ionic compound of some sort, right? If it has all nonmetals, that's going to be a covalent compound typically. All right. So carbon has to make 4 bonds to complete its octet. So if we look at CH4, what we can see is that, well, it has to have carbon in the center, and then it has to have 4 hydrogens around it, all bonded to the carbon with single bonds. There's no other arrangement that can be. Okay. And if we write that on paper, what we would see is we would write it like so. This is represented, called a Lewis structure. Okay. I'm going to discuss how to draw out Lewis structures. The way I typically do this, and I recommend you do this, is typically a little different than what you'd see in from other professors and other teachers, okay? My methodology for doing this has an extra step in it, but it makes it so you never need to know anything about what you're doing. You'll always get it right no matter what. You just have to follow the procedure, okay? I like things you can do at 5 o'clock in the morning and have no idea what you're doing because you're so tired. I like to do that because I was short of sleep all the time. All right, so drawing Lewis structures for covalent compounds. This is your book's methodology. Step 1, you're going to draw the correct electron dot symbols. Step 2, line up the atoms. Step 3, draw the Lewis structure. Step 4, confirm the valence shells are complete. Step 5, check your structure. Okay, let's go ahead and do my methodology real quick, and I'll show you that one. You can see which one you'll end up doing. Realistically, all I care about is you pick one that actually works for you. Okay. But usually that ends up being my method. Okay, so my method works like this. Let's go ahead and do a formula, and I can just guide you through my method. Okay? We have a formula now. Notice it's the same one I was talking about with sugar. You buy everything, most common denominator. That's poisonous. It's not good for you. Okay. At least not too much of it. Now, the first thing I'm going to do is I'm going to count up my number of valence electrons. Okay? And so my carbon, how many is there? 4. Very good. My hydrogens, 1 each. There's 2 of those, right? My oxygen, 6. Very good. Okay, and all together I end up with 12 electrons. Okay, the next thing I'm going to do is I'm going to find the thing that's furthest from being a noble gas. Okay? I'll look at my periodic table. The thing that's furthest from a noble gas is carbon. Everybody say okay? Okay, so carbon. Around that, I'm going to line up all my other stuff and create a single bond to it. Okay? And so my hydrogens have to be connected to that somehow. And my oxygen needs to be connected, right? Now, if I have an indication that one of these needs to be connected somewhere else, then I can remove it and move it there, okay? But if I don't have any indication, I'll just go. All right, always do this with something you can erase, okay? Because my method is going to require an erasing if we have some issues, okay? Now, the next step I'm going to do is I'm going to say I used how many electrons so far? Well, 2, 4, and 6, right? And so I have 6 remaining. Okay. The next thing I'm going to do with my method is I'm going to go around all the outer stuff. I'm going to add electrons into its valence shell until it is full. Okay? Hydrogens are already full at 2, aren't they? So those are full. Oxygen needs how many to be full? it needs 8. Okay. So if I look at its period, it needs 8 to be full, or another way of saying that is it needs an octet, right? And so notice that uses up the remaining 6. Okay. Okay. Now what I'm going to do is I'm going to go through and do I have all of the octets full? Do I have all of their valence shells full? Are they isoelectronic to a noble gas? Okay. This is full. This is full. I'm good there, aren't I? That one's full. I'm good there. Is carbon full? No, carbon's short, isn't it? Carbon only has 6. It should have 8. This is where the important difference between my method and Rayleigh method comes in. I'm going to take any lone pairs that are on these ones that are attached to the center. I'm going to move them into bonds with the one in the center until the one in the center is full. Okay? And so I moved one of the lone pairs here into that double bond.
Wouldn't the hydrogens have to, or
They do.
they have the line?
Right here, yes.
Or are they supposed to have one now?
No, it's noble-like configuration. So the noble is helium, which has 2. Okay? Or another way of saying that is hydrogen's octet just has 2. Okay? Does that make sense? Okay, so now everything's full, and I have my double bond. And so that structure's done. I'm good to go. Congratulations. Okay. I have extra videos showing you how to do this loose structures. There's actually 4 of them up on my YouTube channel, and I'll take you through examples of like every single type of them. Okay. If I end up not getting a chance to do that, okay. I think I'm almost out of time. Okay. Does anybody have any questions about this so far? No? Okay, fantastic. That will actually work on every structure, and you don't have to guess if it has a double or triple bond because you have that step where you'll take things into double or triple bonds. So you never have to guess. Okay. Most other professors would show you a method where you'd have to guess the double and triple bonds. And then you never know if you're right, and you're always like, whoops, messed that one up. Now I have to redo everything. Okay, let's talk about naming covalent compounds. Now, in binary compounds, these are going to be composed of only 2 elements. That's where the binary name comes from. And they're going to be named by a 3-step procedure. So you're going to name the first element in the formula. You'll name the second element in the formula. And then you're going to change the ending to "ide." Notice it's very similar to the ionic, isn't it? You'll designate the number of each element present using one of the Greek prefixes. Prefixes are those first parts of the word that tell you the number of things. For example, bicycle or monocycle. Okay? Those are Greek prefixes. Okay, let's go ahead and look at some examples. There's kind of a fun thing you can do with this, by the way, that like is a common thing all my classes tend to do every few years. So some compounds, we have water here. This is ammonia, and this is nitrous oxide, okay? These are their traditional names, and they're widely used, but they do have chemical formula names. First, I need to give you these right here, the Greek prefixes. Mono means 1. Di means 2. Tri, like tricycle, 3, right? By the way, bi and di are just because the back in the day they weren't sure which we should have done for English. So bi and di are realistically the same thing. Tetra, like tetrates, right? 4. Penta, like pentagon. Hexa, like hex wrench. Hepta, 7. Heptagon, I guess. And then octa, 8, but you rarely ever get up to 8. It's extremely unusual. Okay, so what would H2O be named? Think about that, and I'll do the fun thing next time, okay? Dihydrogen oxide, but we'll do the fun thing next time, okay? Okay, what if I told you that there's this horrific drug, 100% addiction rate? Everybody that's ever used it is addicted to it. It's called dihydrogen monoxide. It causes more property damage than every other substance on the planet combined. It kills more people than all other substances combined on the planet. And so what people do is they like prey on the fact that people don't look stuff up. And I've actually had people do this on Facebook and like start a band that they want to ban water. And then one of my students actually had his mother, he was like laughing about it, and his mother like stopped speaking to him for a week. Because she's like, you shouldn't laugh about something so horrible.
But